In this lesson, you will learn how to name alkanes, how to draw isomers and discuss the properties of isomers, and you'll learn how to name and draw cyclic alkanes. We're going to be starting on page 6 in your booklet, so you're going to want to turn to that page. On this page, we are going to go through the systematic steps that we take in order to name an alkane. We're going to be making reference to the tables on the previous pages 4, 5, and 6, where there are the important prefixes and isomers of the substituents. The way that we're going to approach this is by doing one example that's given to you in the note and following it through based on the steps. And then we're going to do a second example together. Here are the steps just listed in order, but what we're going to do is go through them one at a time and analyze this particular molecule. At the moment, you should have a bit of a picture of the name of an organic molecule in your head based on the examples that we've done in class. So you'll recall that the name always ends with the parent chain. So the last word in the name tells you the main part of the molecule. And then in front of that, we describe the substituents or the branches that are coming off of that main chain. Now, when you're presented with a molecule to name, the first thing that you need to do is to identify that parent chain. And the parent chain is going to be the longest continuous chain of carbons that you see in the molecule. And it's not always going to be the longest chain going from left to right, because as you've seen from working with the models, these molecules can twist around and get tangled. So when we're presented with a molecule, we always need to count and find the longest continuous chain of carbons. So for example, if we start at the top here, 1, 2, 3, 4, 5, 6, 7, that's the longest chain. If we went any other route, we would encounter a smaller chain. In referring to the prefixes, you know that this longest chain has the prefix hept, referring to the fact that there are 7 carbons. Because this is an alkane, or there are all single bonds, the ending is going to be ane. So this is going to be heptane. Next, we need to identify the substituents that are attached to the main chain. And we've got 3. This one here has 1 carbon, so this is a methyl group. This is 2 carbons long, so it is an ethyl group. And this is also a methyl group. Now, as you'll recall, we need to, in our name, state the locations of the substituents. And this is probably the hardest part of naming organic molecules. It is to decide which direction we're going to count on our longest chain in order to identify the positions. When you've got an alkane, what you actually need to do is check the positions counting in both directions. So if I go in this direction, the substituents are on carbon 2, 3, 4, and 5. If I go the other direction, so starting down here, my substituents are on 1, 2, 3, 4, and 6. Now, in order to be systematic, the rule is that we will select the lowest set of numbers. If you have a set of numbers and you're not sure, by looking at them at first glance, which one's going to be the lowest, if you take the sum of all of them, you're going to be able to decide which one will give you the lowest set. So for example, here, this sums to 11, while this sums to 13. So this confirms that we're going to number from top to bottom here. So this is on the second carbon, this is on the 4th carbon, and this is on the 5th carbon. Now that we've decided the appropriate positions, we can put the names of the substituents out front. And you'll recall that in a name, we put them in alphabetical order, and we're going to put them in alphabetical order based on the number of carbons in the substituent. So at this point, I can decide ethyl is going to be first. So my name is going to be 4-ethyl dash. Now the methyl is repeated twice, so I don't need to put 2-methyl 5-methyl. I put it together and say 2, 5 dash dimethyl heptane. So a few little tidbits about putting a name together. We always use a dash to separate a number from a letter, and we always use a comma to separate two numbers from one another. A lot of the times you'll see no space here. It's appropriate. You can choose. You can put a space or not put a space. Some people prefer it one way, others the other way, and that's fine. Okay, so that is the name of that molecule. Now what we're going to do is do one more example together. So the first step is to find the longest continuous chain of carbons. So you can check all the different routes going this way, going that way. In this case, 1, 2, 3, 4, 5, 6, 7. I've chosen another one that has 7. So the parent chain in this is going to be heptane again. And we've got 3 substituents. So we've got a bromine, we've got this group, and we've got this group. Okay. So bromine, you'll recall to name a halogen. You take bromine, you drop the INE, and you add O. So this is called a bromo. This one is 2 carbons long, so it's called an ethyl. This one has 3 carbons in it, so it's called a propyl. Now the fact that this is not in a straight line, it's got a different arrangement of the atoms, this is an isomer of a propyl that would look like this, where we've got the 3 carbons in a row. If you look at page 4 in your booklet, you can see the chart that has a small list of the isomers of substituents that you will be working with. So if you refer to that table, you can see that when you have a propyl with the atoms arranged in this way, it is called isopropyl. Now in terms of the numbering, numbering from left to right, the substituents will be on 1, 2, 3, 4, 5, and 6. Okay, so numbering that way. If we number from right to left, they're on 2, 3, and 4. So this is the direction we are going to name. In terms of alphabetical order, bromo will be first, followed by ethyl, followed by the propyl. So our name becomes 2-bromo dash 3 ethyl dash 4 dash iso. I'm running out of room here. Isopropyl heptane. So that is the name of that molecule. We'll just take a moment and refer to the chart of branched alkanes. So this is on page 4 in your booklet. So you've seen methyl and ethyl quite regularly. Propyl, there are 2 options for it. So normal propyl is when the carbons are in a straight chain. An isopropyl is when they're organized by attaching to the main chain at the second carbon. R in all of these examples is the main chain, or the parent chain. Now for butyl, there are 4 different ways that butyl can organize itself. Much like propyl, there's a normal butyl where they are attached in a zigzag, just a straight line in a normal way. Isobutyl, it looks like an isopropyl with an extension. Okay? So there is a carbon here, 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 and here. I remember this one because it looks like a capital I when you put it in reference with the parent chain. A third isomer of butyl is sec-butyl, and sec-butyl is when the second carbon of the butyl chain is what links it to the parent chain. So the butyl is attached to the main chain by the second carbon in the butyl. The fourth one is tert-butyl. This stands for tertiary. It looks like a lowercase t. Still has 4 carbons because it is an isomer. Got 1 carbon with 3 methyl groups attached to it. You want to keep an eye out for these substituents, and both in naming and in drawing. Now at this point you can do the exercises related to alkanes in your booklet. They are found on pages 8 and 9. I'm going to show you a strategy for solving one type of the problem that you'll see throughout all of our exercises, and that is one where we're going to identify errors in a name. So I'm doing a completely separate example, but you can see on page 9 that you'll be answering a similar problem. So the question is presented as this: what, if anything, is wrong with each of the following names? If the compound exists, write the correct name for it, and it gives you a strategy. So the strategy that I use is to take the name as it's given and draw it. And then I discard the name and don't look at it, and I name it myself following the steps very carefully. That, I find, is the easiest way to identify any errors. Students who just scan the molecule and try to pick out errors by looking at it will often miss errors, especially if there's more than one. So if we want to draw this, it's no name, so that means 9. So 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. On the 4th carbon, we have an isopropyl, so 1, 2, 3, 4. Isopropyl looks like this. On number 7, 5, 6, 7, we've got 2 methyl groups, so they're separate. And on number 8, we have an ethyl group. So now I'm going to ignore this name, okay, and I'm going to name it myself. Okay, right away I can see that they didn't choose the longest chain. You can't have an ethyl group, which is 2 carbons long, attached to the second carbon. So the longest chain is actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is actually properly called a decane. So when we're making a list, okay, we would write longest chain, not selected. Okay, then I look, I've got 3 substituents that are methyls, and then I've got an isopropyl. So they've named that properly. Now they've numbered it in this direction, 1, 2, 3, 4, 5, 6, 7, 7, 8. Had they numbered it in the other direction, 1, 2, 3, 3, 4, 5, 6, that would have been better. Okay, so they haven't numbered it in the right direction. Now, because our chain is a little bit longer, we're going to start here and number it properly. So 1, 2, 3, 4, 4, 5, 6, 7. So they've numbered in the wrong direction. Okay. Another error that they've got here is they haven't actually put it in alphabetical order. Okay, so this should be first, followed by meth, followed by prop. So remember, when you're putting things in alphabetical order, it's based on the number of carbons. The prefixes are irrelevant here. Okay, so the proper name here, our meth is going to become before our prop, so we're going to have 3, 4, 4 dash trimethyl dash 7 isopropyl decane. So that's the approach to solving those problems. Now at this stage you can pause the video and do the exercises associated with alkanes, or you can keep watching the video and do all the exercises at the end. We've talked about isomers, and we've talked about how they have the same formula but a different structure. And we're just going to talk briefly about properties of the isomers. So when we look at butane, there are actually 2 isomers of butane. We can have the normal butane, where the carbons are in a straight chain, and then we can have isobutane, which is its common name, but if we name it properly, 1, 2, 3, it will be 2-methyl propane. Now when you're drawing isomers and you want to determine if you've drawn a different molecule or the same molecule, naming the molecules that you've drawn is really helpful, because if you have 2 molecules that end up with the same name, you're going to know that you've made an error. So for example, with the isomers of pentane that we were doing, okay, these 2 molecules, although they might look a little bit different, they're actually the same. And if you were to name them, they would both be called 2-methyl butane. The parent chain is 4 long, and then on the second carbon there's a methyl group. So even though I've drawn it in the opposite direction here, this, being the lowest position, is going to be called 2. So 1,2-methyl butane. Now, in terms of properties, normal alkanes are going to have higher boiling points than branched alkanes. And the reason for that is about the intermolecular forces. So if you look at 2 normal alkanes of butane and their interactions with each other versus 2 branched alkanes, there's going to be more opportunity for London forces to occur between these 2 molecules. The branches tend to get in the way, essentially, of the molecules coming close together, and therefore the forces are weaker. Now we're in your note on page 10, and there's a little chart there that shows you how many isomers there are based on the number of carbons. And for butane there's only 2. You saw for pentane there were 3. You're going to draw the ones for hexane. But as we increase the number of carbons, the number of ways in which the carbons can organize increases and increases and increases. And so the number of isomers increases. And it just shows you an example there of how many isomers you can make with the different number of carbons. The exercise that you'll do with this is on page 10, and you're going to draw and name the isomers of hexane. The next type of molecule that we're going to look at are cyclic alkanes. And they're still alkanes because of the fact that they're going to have all single bonds. One of the unique things about carbon is that it can form these long chains, and another unique thing is that it can form rings. So the general formula for these cyclic alkanes is going to be CnH2n, because if we make a ring, we're essentially joining the two ends of the carbon chain, and so we don't need those two extra hydrogens at either end, because we're making an additional carbon-carbon bond. Now, because it's all single bonds, the geometry is still going to be tetrahedral, and the angle at each carbon is going to be 109.5 degrees. So, as you can imagine, the angles, the strain of these cyclic hydrocarbons is going to increase as we have fewer atoms in a ring. The most stable structure contains 6 carbons, so cyclohexane is quite stable. On page 11 in your notes, you can see a list of some typical cycloalkanes. You've got propane and butane and pentane. And what you'll notice is that we use the prefix cyclo to say that the parent chain has the carbons joined in a ring. The steps are going to be pretty similar for naming. So again, we want to identify the parent chain in a molecule. So when you look at this molecule, the longest chain of carbons is the ring. Now, one thing that's really important to note is that we don't start outside the ring and go around the ring when we're trying to find the longest chain. Your longest chain is either going to be a ring of carbons or it's going to be a chain of carbons. So in this case, our longest continuous chain is the ring, and there are 5 carbons. The prefix for 5 is pent. Because they're in a ring, we're going to use another prefix, cyclo, and because it's an alkane, we're going to use the ending N. Ane. So the parent chain for this molecule is cyclopentane. Now the substituents on this molecule, or the attachments, we've got a propyl group, and we've got a methyl group. Now, because we've got a ring, we still want to achieve the lowest possible numbering, but whether we number from left to right or right to left, we're going to be dealing with the exact same numbers. So I can start and name any one of these carbons carbon 1, but because I want the lowest numbering, one of the substituents is going to be 1. So I can go 1 and 2, or I can go the other direction and say 1 and 2. The way that you decide which one gets the priority or which one gets the number 1 is by identifying the bulkiest group. So in this case, the propyl is the bulkiest group, so it's going to have the number 1. So this is going to be 1 normal propyl, and this is going to be 2 methyl. Alphabetically, methyl is going to come first, so the name is 2-methyl, 1 normal propyl, cyclopentane. And that's the name of this cyclic alkane. Now, it is possible to have a cyclic group as a substituent. Okay, so for example, if I've got this chain like this, with this group attached, my longest continuous chain of carbons is 1, 2, 3, 4, 5, 6, 7, versus 1, 2, 3, 4. So the parent chain here is going to be heptane. And this group is going to be named as a substituent, 1, 2, 3, 4. It's on the 4th carbon. If it was on its own, I would call this cyclobutane. cyclo for the fact that it's in a circle, bute for the fact that there are 4 carbons, and ane for the fact that it's an alkane. Because this is a substituent, I'm going to change the ending to YL. So this becomes 4-cyclobutyl heptane. So at this stage, you can complete the exercises on page 8 and 9, 10, and 12 and 13. And that concludes this lesson.